Good morning. Assalamualaikum and welcome to our joint lecture series. So today talk number 3 will be given by my friends, Dr. Muhammad Ir-Wan, who is currently a senior lecturer in University Malaysia Pahang. He graduated with a degree in civil engineering from University Science Malaysia in 2008. After which he worked as a graduate engineer in a consultant in Shah Alam, which is Zari Associates Senayan Berhad. So for those who would like to know more about designs, not only involving static loading but also dynamic loading, you may personal message or ask Dr. Ir-Wan later on. Okay, after some years working, he continued his master in University Science Malaysia and graduated in 2012. Following which he directly pursued his PhD in earthquake engineering and graduated from University of Science Malaysia with PhD in 2016. Dr. Muhammad Ir-Wan is professionally registered with IEM, Institute of Engineers Malaysia, Board of Engineers Malaysia, as well as the latest one is the Malaysian Board of Technologies, MBOT. Throughout his research and previous work experience, Dr. Ir-Wan has managed to accumulate and gather VR expertise, especially in earthquake engineering, seismic design according to Euro 8, for which we also have to focus on Malaysian National NS, and then repeated earthquake simulation using finite element modeling simulation. Cyclic loading test, this one involves laboratory testing, and also cost engineering with special focus on the structural works. Therefore, without further ado, I would like to welcome our esteemed speaker today, Dr. Muhammad Ir-Wan, to share his knowledge with us all. You are most welcome, Dr. Ir-Wan.
Okay, thank you very much to our chairperson today, Technologist Muiz from University of Malaysia Perlis. Okay, Assalamualaikum and very good morning to everybody. Thank you very much for joining my lecture session. Okay, I will talk about evaluation on structural performance considering the repeated earthquake. Okay, this is the presentation outline. Okay, I will talk about the earthquake action on buildings, structural damages due to earthquake, performance level, ROMO code to the program, and into the output of the program, which is the inter-story drift ratio. Okay, first of all, we must understand about the earthquake actions on the buildings. The nature of the seismic forces is it's originated from the inertial forces, okay, which is generated when the mass of the building try to resist the ground accelerations. The horizontal accelerations transfer up through the superstructure and generate the inertial forces throughout it. Okay, let's say this one. Okay, actually the building is static. The building is static originally, and then when the earthquake strike the site, it will cause the ground movement. Okay, we can measure in form of accelerations, velocity, and the displacement. Okay, it will accelerate the ground, and then this part of the building will remain static, and it will generate inertia. Okay, this is the comparison between gravity forces, gravity load is it act vertically, and the inertial forces will act horizontally. For simplicity, the inertial forces are assumed. Okay, the simplicity okay, to simplify, okay, your understanding, the forces are assumed to act at the center of mass at each floor. Okay, this is the distributed inertial forces in the floor, columns, and walls. The forces come from the masses of the building, which is from the dead load of the structural elements, and also the imposed load. I mean the partial imposed load. We not consider whole imposed load. What we consider about 24 to 30% only during the earthquake. Okay, it distributed okay throughout the building from the masses, from the weight of the element, and then we assume it become as masses. Okay, on the whole story. Okay, and then for further simplification, the initial forces shown acting externally. Okay, from this one, from this direction, and also later on from this direction. Okay, because the forces, if you still can remember our physics knowledge in Tangerang 4, M times A. Okay, this is the forces, and the masses is the weight of the building plus the imposed load, and the acceleration is from the time history record, which is we record the time history, we record the accelerations against the time during the earthquake. So this is the comparison between the wind action and the earthquake actions. The wind action is when the wind blow to the building, it will act as a pressure to the external cladding or external brick wall, and then we will distribute the load to the joint. But the earthquake load, it originated from the initial forces and that is strongly influenced by the amount of masses and the amount of accelerations. Okay, here is some factors that affecting the severity of forces, which is the weight. Okay, as I mentioned before, the Newton's law, the force is proportional to the weight. F is equal to ma. So we try to be as lightweight as practicable. Okay, as an example is we replace heavy masonry interior wall with the lighter material in order to reduce the masses, and at the same time we can reduce the forces. The natural period also affecting the severity of forces as well as the damping response spectrum and the level of ductility. Now we take a look on the structural damage due to earthquake. Okay, this is the typical damage due to earthquake on buildings. It can be divided into two, which is the damages on the structural system and damage on the non-structural systems. For RC building, for moment resisting frame system, the damage is can be observed occurred on the beam, column, and on the beam column joint. For the non-structural system, the damage usually occurred on the brick wall and the partition, and as well as the shielding, where the shielding will fall down. Okay, this one research from Baraktar et al. Mentioned that the structural damages occurred on RC buildings as a result of earthquake actions, mostly associated with the following reasons. This is the main reasons, among the main reasons of the structural damages. They say the soft story failure, strong column, weak beam design, short column effects, lack of transverse reinforcement in the beam and column. Let's say this one is the joint of the beam and column. Transverse reinforcement means your link. Okay, let's say this is your vertical bar of the column, and this is your horizontal bar of your beam. So let's say non-seismic design, the spacing is too wide. Okay, and for seismic design, okay, in order to reduce the damage, we must reduce the spacing of the link, okay, or we call it as the transverse reinforcement. So the link will become closer in order to confine the reinforcement. And according to Eurocode, for ductility class medium and ductility class high, we must also provide the link within the beam column joint. Then the confinement reinforcement, okay, this one, as I mentioned before, the confinement reinforcement in beam column joints did not exist, but for seismic design, we must provide the link within the joint. And then the existence of short lap splices and incorrect end hook angle. Okay, let's say this one, especially in link. Can you imagine this is your link and this is the main bar. So the end hook angle should be like this one. Okay. But sometimes in construction, to simplify, they will just end up like this one. Okay. Let's say this is a column, so this one is weaker, this one is weaker than this one. Okay, poor quality of concrete, inadequate safe distance between buildings, which result in pounding effect, and also the use of unribbed steel reinforcement, which cause weaker bond between concrete and steel. So for seismic design, we prefer the use of steel bar, which have this one, the rib bar, okay, not the rounded bar. And then what species of strength reinforcement led to shear failure, buckling of longitudinal reinforcement, and then the poor confinement to the concrete core. That's the main reasons of the structural damage to RC buildings. Now we take a look on the performance level. Agak laju ke? Itu masih okey lagi? Okay.
Should be okay, Dr. Ir-Wan.
Okay, this is the Shinkansen bullet train. Okay. Okay, the performance level. Okay, what is the performance level? Because today I'm talking about the structural performance. Okay, we must evaluate the performance level to determine the status of safety of the building after the earthquake. Okay, it will show the performance of the buildings against the earthquake, and this is very important so that the status of the building can be declared either it is safe for use, need repairing work, or has to be demolished. And according to FEMA 356, there are three main structural performance levels, namely as the immediate occupancy, life safety, and the collapse preventions. And actually we have one more, which is, we call it as operational. Okay, this is the number 4, operational. And then all these performance levels can be measured based on the inter-story drift ratio. Okay, this is from FEMA 356, the level of damage, and then the indicator. Okay, level of damage and then the indicator. This is the primary damage and the secondary damage. Let's say the minor spalling in a few places in ductile column and beams. And then when it comes to lateral life safety, it will experience extensive cracking. And then for collapse preventions, it will undergo extensive spalling in columns. And in form of inter-story drift ratio, ada yang nak join ke? Any participant, any new
So
participant?
far tak ada yang baru. Should be
Okay,
okay.
this one. Sorry, because
Ada.
okay, I just approve them because I'm the owner of the
okay.
I set up this one. So if I open any applications, so the others cannot join. It's okay. Okay, it's okay. Just tell me if we have another participant. Okay, thank you very much for joining us. If I'm not mistaken, I also have Dr. Ir-Wan Lim from ITB. Dr. Ir-Wan, are you with us now?
Yes, I'm with you.
Okay, Pak Ir-Wan, sehat?
Sehat, alhamdulillah.
Alhamdulillah. Okay, but condolence
Also,
to
some students from Indonesia.
Okay, alhamdulillah. Thank you. But make sure they are waiting until the end of the session because I have some quiz.
Oh, okay.
I have some quiz. But
Sure.
first of all, condolence to Indonesians because due to the submarine which submerged in the sea of Bali Ocean.
Oh yeah, thank you.
I'm also sympathy and empathy for that victims.
Yeah, thank you so much.
Okay, can we continue? Sorry for the interruptions. Okay, for the immediate occupancy performance level, the inter-story drift ratio will achieve the 1% of 1% of drift, and then 2% for life safety, and 4% of drift for collapse preventions. For operational, okay, the drift is equal to 0.5%. Okay, where the building can be operate immediately after the just after the earthquake. We can use the building immediately without further checking. Okay, but it must achieve at least not more than 0.5% of drift. Okay, here is the performance level. Okay, the inter-story drift ratio is the relative displacement of adjacent story normalized to its story height. Let's say this is story number 1 and story number 2 and story number 3. So the performance, the inter-story drift ratio for level number 1 is the displacement of here. Displacement, let's say this is point number 1, this is point number 0. Displacement, the lateral displacement of here minus, okay, the bottom, okay, the displacement at the bottom, and then we divide by its corresponding story height and multiply by 100. So it will become we will get the value of inter-story drift ratio. Okay, this is an example of 3-story RC model. I compare the performance between soil type B and soil type B and soil type B, and this one is for level number 1, level number 2, level number 3. You can observe here that the maximum inter-story drift ratio occurred at the bottom part of the building, where it reached 0.75% for soil type B, and it performed better if it's located on soil type B, where the value is only 0.5%. Okay, let's do some exercise, okay, to avoid from sleepy. Okay, let's say we have a 3-story building where the number of story is equal to 3.3 meters. H1, H2, and H3 is 3.3 meters, and the lateral displacement is given here, okay, as 0.132, 0.208, and 0.314. Okay, how to calculate? First of all, I always, okay, in my subject, I advise my student to do it in form of table, like this one. Okay, like this, we just write down the value of lateral displacement here, and then we measure the value of drift. Okay, can student help me to fill in this form? To fill in this form, what is the value here? Any students? Okay.
0.132.
0.132. Okay. Oh, sorry. Okay, we will start from the top first. Okay, 0.106. Okay, how about this one? The second story.
.076.
Okay, good. And then the last one.
0.132.
Okay, good. So I hope you know how to calculate this value. This one is 0.314 minus 0.206. Okay, because this is the story number 3 and this joint number 2. Okay, this is the value of displacement at joint number 3 and joint number 2. This is the displacement. And then this is the H3, which is equal to 3.3 meter. Okay, can you calculate to me this value? Okay, story number 3.
3.2.
Okay, 3.2. Story number 2. 2.3. And then?
4.0.
Okay, 4.0. Okay, sorry. Okay, 4.0. So then you can convert to you can draw the graph of inter-story drift ratio, okay, which is the level against the IDR, okay. So for story number 1, it's 4.0, so it will be here. And then story number 2, for story number 3, is here, okay. And then you can know, okay, may I know what is the performance level of this building?
Collapse prevention.
So collapse preventions, okay, or CP, okay, collapse preventions. Why you choose collapse preventions?
Because the IDR highest is 4%.
Okay, the highest IDR is equal to 4%. So at this level, what you propose for this building? Is it suitable? Is it
Demolish.
suitable to be used anymore? No.
No.
Okay, so you must propose for the building to be demolished because the repairing work is will be very expensive because the column almost loses its ability to cater for lateral load and even for gravity load. It's very difficult to repair, so it is recommended to demolish the building. Okay, how about exercise number 2? I give you 5 minutes to settle. You have the answer? Anybody have answer from this one? May I hear the participant from UMS to answer for this one?
Anan ada Anan,
Sorry?
Haziq,
They say
Anan.
okay, UMS,
UMS.
this one, okay, UMP,
Hello.
this one Unimet lah, Unimet,
Is it?
and this one UMP. ITB, we have participants from ITB. Okay, this one UMS again. Unimap. UMP again. Kita tak payahlah, kita tuan rumah tak payahlah. UMS. Oh, this one ITB. Okay, UMS. Unimap. And then ITB again. Okay. Any volunteer from UMS to answer this one?
Hello.
Hello.
My name is Anand. I'm from UMS.
Okay, congratulations. What's the answer?
My answer is 0.116.
0.116. Okay, exactly that this one.
0.116.
Okay, congratulations. So how about Unimet? Any volunteer? This one?
Ikmal, sila.
Assalamualaikum.
Salam. Okay, siapa nama?
My name is Ikmal. I'm Ikmal Hakim.
Ikmal Hakim. Okay, what's your answer?
Answer is 0.122.
0.122. Okay, congratulations. Anybody from UMP?
My answer is 0.086.
0.086. Okay, congratulations. Anybody from ITB? Anybody from ITB?
Hello, sir.
Hello, what's your name?
Gusti Kusuma, sir.
Okay,
My
Mr.
answer is
Kusuma.
0.076.
0.076. Okay, congratulations. Okay, thank you so much. From UMS again?
Anan lagi.
0.182.
0.182. Okay, what's your name?
Dayang Marina.
Okay, thank you so much. Okay, from Unimap again. Anybody from Unimap? The interstory drift ratio?
3.5, sir.
3.5. Okay, good, thank you. And then from ITB? Anybody? Similar person is still okay, acceptable. But not Pak Erwin lah.
Hello, sir.
Okay, hello.
My name is Andy from ITB.
Okay, Andy.
Hello, can you hear me?
Okay. What is your answer?
Hello.
Hello. Yes.
My answer is 3.7.
3.7. Okay, congratulations. Thank you very much. And from UMS? From UMS?
2.6.
2.6. Okay, may I know your name? Your name?
Yang Marina.
Oh, it's okay. Thank you. Thank you. Sorry, I cannot see the screen since full screen is from PowerPoint. Okay, Unimet.
2.1, sir.
2.1. Okay, what's your name?
Ikmal.
Ikmal. Okay, good. Okay, and last one from ITB. Okay, your answer, please. Who's the first to answer this one? Andy or okay, any answer here from ITB?
Hello, sir.
Okay, hello.
Sandy again. Yeah.
Okay, good.
4.55.
4.5. Okay. Okay, 4.3 I got. Is it okay? Semua dapat 4.5?
Oh, sorry.
4.5 or
I think
4.3?
the height of first story 4 meter is right.
Sorry, first story is?
4 meter.
Sorry, per type?
The height of first story is 4 meter. No.
Sorry, I
4.2 meter.
4.2
Oh,
meter.
4.2. Okay. I missed that.
Okay.
Okay,
So
thank you.
it's 4.2 meter, it must be lesser lah. Okay. Okay, let's say text look here. Okay, 4.2 meter. Okay. Okay, that's good. Okay, so how about the interstory drift ratio? So the graph will be this one. Okay, you just follow the value given by the table. Okay, and then may I know what is the performance level here? Anybody? Okay, what is the maximum? Maximum is 4.3. It exceeds the 4%. It exceeds 4%, so the performance level shall be?
Collapse
prevention.
Okay, collapse prevention because the IDR is equal to 4.3%, greater than 4% as limit by the code. So also like the 3-story building, okay, is proposed to demolish. Okay. Okay, thank you for your participations. Okay, and this is okay from this part to this part. I will talk about on how to get the story displacement from based on the I'm using ROMO 2D program and a simple 3-story building. Okay. In our exercise just now, I already give you the value of displacement at the bottom, at the point number 1, point number 2, and point number 3. I already give you the value. But in a real world situation, how to get the value of lateral displacement is all here in this story. Okay. Okay, we start still fresh. Why not we start? Okay, I introduce to you the ROMO program, which is developed by Professor Dr. Atal J. Carr from the Department of Civil Engineering, University of Canterbury in Christchurch in New Zealand. It is specifically developed for evaluation on structural response subjected to dynamic load like the earthquake. It is a powerful program to run the nonlinear analysis with more than 50 hysteresis rules available to choose. Okay, I believe Dr. Ir-Wan from ITB expert about the hysteresis rules. And it is a text-based programming where we use text format as input. However, okay, it's quite boring to use it because it's not a graphical base. But however, it is powerful, okay, powerful program to run the nonlinear time history analysis within a very, very short time. Okay. If you use a graphical base, okay, it may, let's say, if you use graphical based software, it will go for hours, but by using the text-based program, it will settle your simulation but within a few minutes only. Okay, in the market, we have a few text-based program to run the simulation of nonlinear time series analysis. One of it is the ROMO. The ROMO we have the 2D and then the 3D, and then we also have the OpenSys, and we also have the iDAC 2D. Okay, this is okay. Anybody interested to use the software and set up your own programming? Okay, this is good. Okay, another one is graphical. Okay, the graphical base, where you can see the graphic view of your model. Okay, let's say this is tab 2000. You also have the e-tabs, and also you have the okay, let's say esteem, but esteem is just for design. Okay, you cannot do the time linear non-linear time analysis with esteem. Okay. Any new participant to join? Okay, no participant. Okay, so in ROMO 2D, okay, as an input, we have a basic of 8 main sections as input models. Okay, the section A is for the basic structural informations and analysis options. Section B is the nodes, okay, nodes arrangements to perform the join of structural models. This is the setup on inter-story drift output in section C. Okay, and then this is the section D is the descriptions of structural element which link between two nodes. Section E is the properties, okay, nonlinear properties of structural elements. This is very important. And then section F is weight, section G is loads, and section H is the earthquake, which is the declaration of paths of ground motions records to be found in the nonlinear time history analysis. Okay, so to simplify, the ROMO 2D program require the input model, which is the detail of structure, type of analysis, up to weight and load. Everything is in text format, and we must also provide the earthquake data, which is the earthquake record from the accelerations versus the time. And then we run the analysis. The ROMO 2D will present to us the results in form of joint displacement, and it will calculate the value of inter-story drift ratio. So we don't have to calculate again. Okay, it will present the value of inter-story drift ratio directly. Okay, so let's take a look on the model input. Okay, let's say I have a 3-story 2D frame. Okay, we have two type of beam. Beam number B2 is at the roof, while beam B1, labeled as beam B1, is located at the first and second floor. And also we have two type of column, which is C1 located at the exterior part of the building, and C2 is located at the interior part. And this one is the detail for C1 and the C2. You can see the difference between these two columns. And the fundamental period of vibration is estimated as 0.5 seconds by using the model analysis. Okay, and this one is the detail for the B1 and the B2. The detail is very important, okay, because let's say this is for B1, so it's located here. So every section here, okay, okay, which is near the column joint, which is in the plastic hinge region, okay, we call it as plastic hinge region. In the software, we must declare what is the properties here, okay? The stiffness, the strength, and so on. Okay, so you must use this section. Okay, this section is located here. For B2, is located here, okay? Near the beam column joint. Okay, as well as for the column, it located here for C2. Okay, since this is 3-story building, so it's similar. If you have higher story, maybe you have a different amount of reinforcement. Okay, so what we do is this 3-story, we must numbering the nodes, the elements, and the section properties. Okay, let's say this is the nodes. We have number of nodes. Okay, I mark as the circle. Okay, the numbering covered by circle here is the number of nodes. Okay, all the circle here, number 1, 2, 3, 4, up to 16. So we have 16 which will join the beam and column, and the number in square here is the number of elements. Okay, we have number of elements is 1, 2, 3, 4. We have 18 elements here of beam and columns, and this is the number of section properties. Okay, section properties is depend on the design of your B1 and B2, and also your C1 and C2. So let's say this one, this beam, the beam here have similar properties with here and here. Let's say this is the number of sections. Okay, the beam here have similar properties is here and here. Okay, this one also here and here, because this one maybe because this one, okay, this is because the numbering, okay, numbering and the properties here, maybe we use a lesser reinforcement. Okay, and this is the column for column number 1, and then column number 2 up to, okay, we have only 2 properties for column and 6 properties for beam. Okay, and this is the basic. Okay, the section A, you must fill in all 5 lines, which is the description of the structure, and then the principal analysis options, the frame control parameters, up to the iteration control and wave velocities. Okay, I'm not going to teach you one by one about how to use the ROMO. The today's class is just introduction on the structural analysis considering repeated earthquake. If you want to know more about this one, okay, maybe we can have another sessions. Okay, maybe we will take around 2 or 3 days. Okay, you can refer to the ROMO manual. Okay, the manual will give you this one. Okay, one by one. Okay, from the, okay, let's say line number 2, we have A until I column, and then the A is I panel is number 2. Why I choose number 2? Because I want to perform the dynamic time history analysis. Okay, let's say we have your I plus is number 1, is the inelastic time history analysis, and so on. Okay, so let's say this one. Okay, from the ROMO manual, it will give you, okay, why you choose number. Let's say I panel is 0. If you put 0, this is the static analysis. If you put number 1, this is static analysis, static and model analysis. So you must choose your option here. Okay, also this is the frame control parameters. This one, okay, output and plotting control. You can refer to this manual. Okay, one by one. What is the number to choose? Okay, also this one. Okay, instruction B is your node arrangement to perform the join of the model. From this one, you convert to the text. Okay, let's say join number 1 is done. Okay, join number 1. Okay, this is, okay, can you imagine the Cartesian, okay, X, Y, and Z. Okay, the X is 0, this is 0, 0. So this is your 0, and this is also 0. Okay, this is your support. Okay, number 1 is for fixed and 0 is for free. So you can see that joint number 1 up 2, 3, and 4, all 4 joints is number 1 because this is a fixed support. Okay, and also let's say joint number 7. Where is joint number 7? Where is joint number 7? Okay, so this is location is 10 because this is 5 meter and 5 meter. So the coordinate here is 10 and 0, and then this one is 10 and 5, as 10 and 3.3. Okay, because the height is 3.3, so the coordinate here is 10 and 3.3. Okay, this means that the joint number 5, okay, this is the joint number 5, which is the master joint. Okay, which is the master joint. Okay, means joint number 6 will follow the property, will follow this displacement of joint number 5. Okay, means joint number 5 is the master, and number 6, 7, and number 8 here, we call it as slave. Okay, you see here, up to number 8, 8 will follow number 7, 7 will follow number 6. So if, let's say, if joint number 5 displays around 0.5 meter to the left, so joint number 6, 7, and 8 also will displace around 0.5 meter to the left. Okay, that's what we mean by master and slave. And also, then we must set up the inter-story drift output. Okay, at section number C, we must declare what is the drift output. Okay, it starts from joint number 13, 9, 5, and 1, and then drift angle 13, 9, 5, and 1. Then the program will calculate for you. Okay, so you don't have to recalculate. And then for section number E is the structural elements that I mentioned before. So this is the properties of element number 1, properties of element number 2, properties of element number 3. You must conduct the section properties, section analysis. Okay, I did once in from 2011 to 2014 by using Cumbia program, where we must input the size of structural elements, and then we must give the value of concrete strength, the steel strength, and the combination of steel reinforcement. We must input with that software, but I'm so sorry I cannot demo to you the software because in my laptop here I don't have the Matlab software. We use Matlab to operate this Cumbia. Okay. Okay, so this one, okay, and then this is the section number F, section G for loads, and this is the the path of ground motion. As I mentioned before, we must provide the input of the building model, and then we must also provide the ground motion. Okay. Okay, then this is about the preparation of ground motion records. Any new participants to join? Because I heard the ping. Okay, oops. Okay, sorry. Okay, this is how to prepare the ground motion record. Okay, for the nonlinear time history analysis, okay, here I use 7 ground motion records from each far and near field earthquake. The magnitude is ranged from 6.2 to 7.6. And according to Shaw method, all ground motions are scaled by referring to the spectral acceleration with damping ratio of 5% at the fundamental period of generic models. Okay, here I use single and repeated earthquake. Okay, the case 1 is repeated single earthquake, which only consider the main shock. And case 2 is a repeated earthquake, which consider the existence of foreshocks, main shock, and aftershocks. Okay, for the aftershocks, we scale down, multiply by 0.8526, because the foreshock and aftershock usually lower magnitude than the main shock. So this is the ground motion records for single earthquake, and this one is the for repeated earthquake. 100 seconds of time gap is provided between all these records in order to give time for the structure to cease from the vibration. Okay, this is the example of ground motion record I selected for this study. Okay, I consider soil type B, okay, far field and the near field. Near field is earthquake is this one is any ground motion recorded between less than 20 kilometers from epicenter is considered as the near field earthquake. So any ground motion recorded larger than 20 kilometers from the epicenter, we consider as the far field earthquake. Okay. Okay, this is how to scale down the ground motions. First of all, each ground motion record has to be scaled up or scaled down to match the real peak ground accelerations on the specific site. Then we scale down or scale up. We refer to the developed response spectrum for the specific site. Okay, this is how to develop the specific spectrum. We refer to horizontal elastic response spectrum. This is from Eurocode 8. Okay, this is the value of soil properties. Okay, the soil factor, the TB, TC, and TD. This one is given by EC8. Okay. Okay, let's say this one. Okay, from National Annex. Okay, my study is here. Okay, I want to study the site specific is here, located here. So the value of reference peak ground accelerations is equal to 0.12 G. And since I consider soil type B, so I consider this parameter. Okay, so this is the elastic response spectrum developed. Since our building, okay, fundamental period of the building is equal to 0.5 second. So we projected here, and then we know that the value of spectral accelerations shall be 0.567. So we must know what is the value of spectral accelerations from the original time history record. What is the value here? We know this value, and then we can know the scale factor to be used, so that the time series, the spectral accelerations for time series record will match the value of the specific site spectra. Okay, first of all, we open. Okay, let's say this is the example of time history record. Okay, from this one is from the Dasker earthquake in Turkey, if I'm not mistaken. Okay, the time step is 0.005, and all this column is this column. Okay, 1, 2, 3, 4, 5. These columns represent the value of accelerations in unit of G. Okay, so we must this is the desktop. Okay, the folder. Okay, the file field original. This one is original ground motion records. So we open by using the SASMO signal program. Okay, the program will give this graph to us. This is acceleration, this one is velocity, and this is the displacement. And then we just click here. Okay, elastic or inelastic response spectra. Okay, it will convert. Okay, it will convert the time history record, convert to the response spectra. Okay, for that ground motions, and then we can select the value of accelerations at 0.5 seconds. Okay, which is similar to our building period. This one, the value here is 0.05772. Okay, 0.05772. So, okay, the value is of original record is here 0.05772. So we want to make it as this one. So we have to scale up or scale down. So the scale factor is equal to response spectrum, okay, at specific site to the divide by the response spectrum value by the original motions. So what is the value? 0.567 divided by 0.05772. Can somebody help me? Ratio calculator. Anybody?
9.832.
Sorry, 9.82.
82.
Okay. Okay, so the scale factor here is 9.82. This means that, okay, let's say this is the original motions. Okay, but to be used for this model, we must amplify. Okay, by using scale factor, we will enlarge around 9 times. Okay, so the value will be 9 times higher. So it will, in order for it to match the value of response spectrum here. Okay. So this one we can, okay, I also used Matlab before. Okay, we built our own program, actually built by Dr. Adi Faisal from UMSU. Thank you very much for his effort. Okay, let's say, and then we must scale. Okay, we must scale one by one. Okay, we must refer to this scale factor, and then we must put down the value of scale factor, and then we save the newly generated ground motions as the single earthquake order, the case 1. Okay, and then for the repeated earthquake, by using, we refer from the works from Professor Hazi Jeju from Greece. Okay, for the main shock, we just use, okay, let's say this is single, R stand for repeated, S for single. So the single earthquake is for R1 to R7, we just arrange the main shock of 1, 2, 3, 4, 5, 6, and 7. And then the fourth shock and aftershock, we just random. Okay, we just random. Let's say this is at 5, S5, S7, S3, S4, S7, S3 also is okay. We just random. Okay, we just generate random combination by using Excel program also available. Okay, let's say 3, 7, S4, S7, okay, S1, S2. Okay, so we will combine all this in as a one ground motion record. Okay, we will combine later. Okay, so this one, how to generate the repeated earthquake. First, we prepare the single ground motion record, which is already scaled. Okay, this is scaled either up or down. We prepare in one folder, and then we also must prepare the zero ground acceleration records in one folder. Okay, another folder is for zero ground motion records. Means this records for 100 seconds. For 100 seconds, the T is from 10, 1, 10 up to 100 seconds. The value of accelerations is 0. Okay, you can see here that the value is all 0. Okay, because we want to provide this one. Okay, this gap. This is 0, so the record is here. Okay, the ground motion record also in text format. Okay, so means let's say this is number 1, this is number 2, this is number 3, this is number 4, and this is number 5. We want to combine all 5 text file to become one. Okay. Okay, this one. And then we prepare empty folder. Step number 3, prepare empty folder for the output of the repeated earthquake record. And then let's say this is the generated, okay, motion number 2, 1, and 7 for repeated of case 1, motion number 1 of case 2. And then we open, okay, this is example of Matlab file developed by Dr. Adi Faisal, okay, in 2010. Okay, we must, okay, this is the open scale file of, this is for 4 shock. Okay, this is S number 2, means single number 2. And then main shock is scale number 1, single number 1, and then the fourth shock is number 7. Okay, we just edit this path, so then the Matlab will find where is our file. And then this is null means the 0 accelerations, and this is the folder. Okay, the path, the product will be sent here by the Matlab program, and then we can write down, okay, anything here as our reference. Okay, let's say if once we run the analysis, the Matlab, it will produce this feature. We can save if you want. Okay, this is the all 3 repeated earthquake, and this is the foreshock, main shock, and aftershock. Okay, this is the foreshock, this is the main shock, and this is the aftershock. Okay. Okay, and then how to run the ROMO Code 2D program. We already prepared the input from our building, and we already prepared our ground motion records. And now is how to run the program. Okay, we have 3 basic steps. Okay, 3 basic steps to run the program. First of all, we must prepare the specific folder for the input for the earthquake. For the input means the model of the building. Earthquake means your ground motion records, and output will be your results in terms of inter-story drift ratio and so on. And then step number 4 is we set the right path in the batch program file, and then we can run our ROMO code program. Okay, let's say this one. We must prepare the specific folder. We must have these 3. Okay, the batch 2D, FQIN, and then ROMO code 2D. This is the programming file, and this is the folder for the earthquake ground motions. This is a folder for your building. Let's say this is N3. This is the folder of your building. As I mentioned before, we have 8 sections for it. We must provide all the characteristic or the specification of the building. And this is the folder for your output data. And then, okay, let's say this is example. This one is for your single ground motions, and this one is for repeated earthquake ground motion. Okay, let's say, so you must have R1, R2, R3, R4, up to R7. If you use 7 ground motion records. Okay. And then this is the step number 2 is we set the right path in the batch program file. We must set up this one. So we give order to the program on up to what level the program has to do the analysis. Okay, this is the total number of ground motion records. Number 1, 2, and 3 means up to number 3 only. Okay, means ground motion, the program only will run for S1, S2, and S3 only. Okay, so if you want to run up to 7, so you must adjust become 1, 2, 3, 4, 5, 6, and 7. Okay, and then this is the, okay, you edit the batch file. You must do, okay. This is the location, okay, location of the programming. Okay, it will find the programming later. And then this one, the edit file for your output. Okay, it will find. It means if you run the S1 for ground motion number 1, it will give you output for also for S1. What is the result for S1? Okay, so you must prepare the folder carefully. Okay, and also this one, this is the ground location of the ground motion record. Okay, so the program know where to find the ground motions for the analysis. And then we just double click this batch2d file to run the analysis. You can see this. Okay, what up to what second the times3 has been run by the program. Okay, if you have long single ground motions, means maybe it lasts around 60 to 70 seconds only, so it will take shorter time to run. But if you want to run for repeated earthquake, it will have a longer time, maybe up to 2 or 3 minutes. Okay, 2 or 3 minutes, depend on your model. Okay, higher number of story or more number of nodes, more number of join will make your model more complicated to settle the analysis. Okay, and this one is the output in terms of inter-story drift ratio. Okay, then as I mentioned before, we must provide the folder for the output, and then the program will send the output here, also in text file, so we can extract the value of inter-story drift ratio. You can see here the positive and the negative envelope. Okay, because our building, okay, move to the left and to the right. Okay, so that's why we have positive and negative envelope. And then this is the data. We detect this data from the output, and then we can extract to single file. Okay, we extract to a single file by using another programming, and then we can convert. Okay, we can open this file to the Excel, and then we can take the value of the inter-story drift ratio. Okay, and then we can present, as I mentioned before, we have 7 ground motions, 1, 2, 3, 4, 5, 6, 7. And for 7 ground motion records, we can take the mean value. Okay, this is the mean value, dash. Okay, we take the mean value as the result. Okay, okay, so this is some comparison between, this is for far field earthquake, and then this is the near field earthquake. Okay, you can see here that for the N3 means number of story is equal to 3. You can see here that the case 2 of repeated always larger than the result for single earthquake. Okay, the same also, the similar result also occur to model run by using near field earthquake, where the result of inter-story drift ratio for repeated earthquake is higher than the single, and it almost reached the limit. Okay, here I want the building to be in immediate occupancy, so the limit is 1%. So it almost reached the limit. Okay, and this one is from the result from 6 story for the far and for the near field. You can see the result is almost similar, almost standard pattern, where the repeated always larger, cause larger inter-story drift ratio than the single earthquake. Okay, this one is for 9-story building, and this one is for 12-story buildings, where you can see here that the maximum story is concentrated at the bottom part of the building. Okay, for both cases, for single and for repeated earthquake, the inter-story drift ratio is concentrated at the bottom part of the building. Okay, now let's do some conclusions. Okay, anybody want to do conclusions? Any conclusions? I can see at least 2 conclusions here. Anybody want to conclude? You just conclude based on the value of inter-story drift ratio. Okay, because our topic here is the seismic performance. So you can conclude based on the result of inter-story drift ratio. Anybody? Based on this result? What can you see? What can you see between the near field and far field, and between the repeated and the single earthquake? This one, right? Okay. Repeated will cause larger inter-story drift ratio than the than the single. Okay. Okay, so you can use the calculation is interest-to-read ratio caused by repeated always larger than the single. And also another conclusion you can conclude here is when you compare the performance of drift between the far field and the near field. Okay, you can see that the value, okay, even subjected to repeated earthquake, the value is here. Okay, let's say this is 0.7% and this is around 0.85. Okay, the maximum. Okay, you can see here, this is 0.7, this is 0.6. Okay, this is maybe 0.7, this is 0.8. Okay, what can you conclude is IDR caused by the near field earthquake is always greater than what is caused by the far field earthquake. Okay. Any other suggestions you want to conclude? Okay, related to the number one conclusions, so it is strongly suggested, okay, in order to evaluate the structural performance, it is strongly suggested to use the repeated earthquake, to consider the repeated earthquake phenomena, because it will give you larger amount of drift. Okay, so you will never underestimate. Okay, you will never miss these situations, because in the real earthquake, okay, the earthquake did not occur just in a single time. Okay, just like what has been presented by Dr. Shina last 2 weeks, that the earthquake will always occur repeatedly. Let's say this one, and then for the after 2 or 3 days, or after 2 or 3 weeks, it will occur another one. This is the main shock, and then the fourth shock will occur again, and then again, and again. So the action of repeated earthquake will cause higher interest-to-read ratio, and then could produce more damage to buildings. Okay, we must consider this one. Okay, because the current practice only consider the single earthquake, and then if we found that the building is passed, and that the design is okay. But however, okay, current situation suggested we consider the existence of repeated earthquake. So maksudnya kita jangan tidak under design. Okay, we are not under design. Okay, so we consider this one. Okay, this phenomena, this is maybe after a few days, after a few hours, it will occur again. Because after the first strike, the stiffness and the strength of the building might be degraded. So it will be easier for these smaller ground motions to cause more lateral displacement to the building. Okay, any questions? Thank you so much. That's all my presentations today. Never give up, dare to dream and dare to believe. Okay, thank you so much.